Okay, to start the year, there's some important vocabulary and some other items for you that I think will be very valuable as you learn them for the entire progression of the year in physics. These things include, but are not limited to, symbols, syntax, protocol, and units. And I'd like to define some of these and give some examples and specific ones that you'll need throughout the year. First of all, symbols are simply the identifying characters that we use in order to communicate. And so in this particular case, we're talking about letters, numbers, and most importantly in physics, vectors. Vectors may be a new term for you. So just to be clear, vectors, the definition is magnitude in a direction. It must include both, or it's not a vector. Magnitude only has its own term called a scalar. Essentially, due to the fact that magnitude in a direction is a vector, and if we think about a number pointing a particular way, we can also generalize as thinking of vectors as arrows, where the direction that it points and the length that it has tells us both the magnitude and the direction. Beyond that, there are a few symbols that will be useful throughout physics. First will be the Greek alphabet. Which I will not get into here. And then lastly is a set of symbols, which do include a couple Greek letters that will be mathematically relevant as well as just comparison useful. And there are 5 that I'm planning on using throughout my discussion, the first of which should be very familiar. This symbol is called an equal sign. And an equal sign simply means exactly what you think it means. Something equals something else. And this is a comparison, essentially allowing us to manipulate algebra, make conclusions about things, etc. The reason why I point that out is a slightly different symbol with 3 lines. This is referred to as a definition. The definition is more like a specific item spelled out by the instructor or the designer that wouldn't necessarily be self-evident in a comparison. Such examples from math exist, such as x squared is defined as x times x. And this will be relevant because, of course, there are other notations such as x with a subscript 2 that would be defined as a different x than, say, x1 or x to the n, if you wish to generically describe it. Definitions are often used when we are reinventing variables or using the word definition of a symbol that may be new to the content that we're working on. This often results in a conclusion, and a conclusion in my notation as well as in mathematical theory is 3 dots in the shape of a triangle. This is the conclusion, therefore. And therefore is exactly what it stands for, is if this is that, therefore this occurs. And this will often be inserted into analysis as we define conceptual physics terms that interrelate, where one thing occurs and then therefore this causes something else to occur. The last 2 are Greek alphabet letters. Capital letter delta is the shape of a triangle, and in Greek this is the delta letter, but in math this means change. And in this particular case, change is defined as final minus initial of whatever the value is. Such an example of change in physics and or mathematics would be something along the lines of change in x, where this would be equal to the final x, say x2, minus the initial x, say x1. While I'm on the subject here, there is an aside in terms of subscripts, which is to say x0, this 0 subscript, subscript is defined as x naught, as in not a number. This would be the lowest value of xn numbers. The last symbol is another Greek letter that's capitalized, which is the Greek letter sigma. Sigma, as a Greek letter, is often depicted like this and can sometimes have sharp edges on it like this. Beyond being a Greek letter, this is used in physics and mathematics to represent the sum, and this would simply be defined as add all items. When we're defining a sum using sigma, we would use the subscript notation as well as a generic variable in order to say add all the x's. So in this case, this would be all the x's given, which would be the initial value plus any other additional values that may occur. Once you have your symbols straight, then we must move on to syntax. Syntax is the format for which the language of your symbols gets coordinated in order to communicate ideas and compare conclusions. In general, this would be the idea behind grammar in a writing or English class or even a history or anywhere really where you're doing written word using verbal speech to paper. In computers, this is the code. This is often binary code in a computer at its most basic level, but all of the programming languages that are used and written by software designers communicate instructions to the computer through code. And then, of course, in physics and math is math. And math is using numbers in order to communicate ideas. And specifically in physics and in physics here, physics 1, we're talking about algebra. And algebra will be your main focus of syntax for this class beyond grammar and written word. We won't be using much computer code, unfortunately, but we will be using quite a bit of algebra. Lastly is protocols. Protocols may be a new word to you, but that is something that you're quite used to in school, which of course is your procedures, your instructions. And your procedures and instructions in physics will often be of two types. One type will simply be written instructions, given out in terms of how to do particular calculations and or instructions for how to complete a particular lab activity. There will also be the idea behind problem solving, which is a protocol system that I've developed for you specifically for solving problems that you don't necessarily understand at first glance. I call this the problem solving process, or the PSP. We'll be talking more about the PSP in another video, but for now, this is to say that this is a protocol designed by me to help you solve problems. Lastly, the final tool that you'll need in order to effectively communicate physics is units. Units are the labels of measurements. The labels of measurements that we use in physics are referred to as the SI system of units. In the SI system, we're communicating using an international measurement system such that all scientists can complete and reproduce physics experiments worldwide. As such, there are a few key ones that we need to point out that are much different than what we typically use here in America. In length, we measure in meters, which will be symbolized with the lowercase letter m. In mass, we will be measuring in kilograms. The SI unit, the only SI unit that contains a prefix in its name, kilograms, will be symbolized kg. This will be the unit of mass. And then most importantly, probably, is time. And time will be measured in the SI system in seconds, symbolized with a lowercase s, but in some cases also written as SEC. These three base units will be used for a huge amount of the early physics in Physics 1, and they will be used to comprise what are called complex units. And it's important to note that complex units, while they are complex, they are simply constructions of the base units of the SI system. And so these will be a combination of base units, which will mainly be these three above. If there are any others as we get into them, we will address them. But an example of this is the unit of speed, velocity, which is measured as displacement divided by time, which in terms of SI units would be meters per second. The units of displacement are meters, the units of time are seconds, as we just talked about above. The units of velocity is referred to as a complex unit comprised of meters and seconds, which is meters per second. Once you have all the units, then you are ready to begin physics.